Welcome to Mechanical Systems Part 2. In the last video, we had drawn a simple picture of an object. It was a large box, 10 kilograms of mass, and it was sitting on a table. And we had drawn a picture showing that there were four forces that we were going to consider. There were two vertical uppy-downy forces. One was the force of gravity, and the other was the force of the tabletop pushing up, which we call the normal force. And those were the vertical forces. And what we did, of course, was we wrote a net force equation to describe all the up and down vertical forces. That's what Y stands for. And we said it was equal to Fn plus Fg. And we realized that F net is always equal to ma, Newton's law, and Fn stays here. Force of gravity was mg, and then we realized that this block would not be accelerating in an upwards or downwards direction. If you push on it, you push it sideways. And so since we're only talking about up and down forces, we realized this would be a zero acceleration, so there would be a zero here. And we had the normal force. We also realized that the gravity force is 10 for the mass, and 9.8 for gravity, and we realized that it would be negative because we had to explain to the math that the arrow is pointing downwards. And so we ended up multiplying that together right here to get 98. We moved it to the other side, and we discovered that the normal force was 98 newtons. And that was what we got from our analysis of the vertical up and down forces. Okay, that was the vertical. Now, in this video, we want to explore a little bit about what was going on with horizontal forces, sideways forces. And we had said that in our picture, there would be a force pushing on the block. We called it an applied force. And then if there's an applied force, there would have to be a force of friction that was working against the applied force, F for friction. So these blue arrows represent the sideways horizontal forces. So this video is all about the horizontal forces and how they influence the motion of the block. So in order to explore this, we should maybe set up sort of a scenario and try and figure out what it is we want to know about the forces that are sideways. So why don't we imagine that there's an applied, well, why don't we figure out how much force you would need to push this block? How much force will we need to push the block? So let's do that. Well, on second thought, let's not. We'll save that for another video. Let's try to keep everything nice and simple. Let's figure out how will the block accelerate. That'll be nice and easy. How will the block accelerate? Because remember, Newton's law says that if there is a net force pushing on an object, it will cause acceleration. F equals ma. So that's what we're trying to figure out. In order to describe how it will accelerate, there has to be some more information given to you. So let's pretend that we're going to push on this block with, let's say 50 newtons of force. So that will be the applied force. Now the frictional force, I'm not going to tell you how much the frictional force is. I'm going to show you how to calculate it, but I'm going to tell you one of the most important parts of friction, which is the coefficient of friction. And remember, that sort of represents the stickiness between the two surfaces, the tabletop and the box, right? How much resistiveness there is between those. It's sort of like how sticky the surfaces are. So let's say that the coefficient of friction happens to be 0.3. So we have these two pieces of extra information that we can use to actually solve a problem like the one we've written. How will the block accelerate? Now don't forget about the vertical forces. We'll need that in a minute. But right now, we only want to look at the horizontal forces. So, horizontal forces are associated with the x-axis. And so what we want to do is we want to figure out how we can write the expression for the net force, this time not up and down, but sideways. So we call it F net x. And so we look at our picture and we try to find all the arrows we can find that are pointing sideways. And of course there are two of them in this picture. There's an F applied and a force of friction. So those are the ones we will use in our expression. Now if you had more, you could put more in. But our example only has the two. So let's put the F applied here and the force of friction here. The net force is equal to the sum of all the forces acting. From the last video, you'll remember that. All right, what do we know about this? Well, in the last video, we said that F net is always ma. And so F net here will also be ma. And that's important because you can see how that's how we introduce acceleration. There's the a, it's showing up here. So now he's in the mix. And of course, the applied force was told to us in the question. It was told to us we were going to push with 50 newtons. And because that arrow is pointing to the right, I will choose a positive 50 newtons. Remember that the pluses and minuses have to be used to tell the math which way the arrows are pointing. Now, you'll recall from a previous video that the way you calculate friction, the force of friction is equal to the mu, the stickiness of the surfaces, multiplied by the force pushing the surfaces together, which happens to be the normal force. And you'll remember normal force was something we were figuring out when we were looking at vertical forces. Now suddenly that normal force is going to be useful because the force of friction, in order to get a number for it, I need to multiply mu times the normal force. Then I have to tell the math which way this normal force is going. And it appears to me that the picture is going to the left. So I can introduce a negative sign here. Or, if you wanted, the general rule that I always use to help myself is to don't put any signs in until you're ready to put in numbers. And since I didn't put any numbers in yet, watch what I do now. No numbers here. I'm choosing a positive sign for the 50. Now I'm putting the numbers in. That's when I also put in the sign for the direction. So we said that the 0.3 was the coefficient of friction, the mu, the funny little Greek M letter. So that goes in for that. That was given to us. And then we look up here and we saw that our normal force was 98 newtons. So we're going to use that for the frictional force. Sorry, for the normal force right here, 98 newtons. So that's useful. And the negative sign to show that the force was going to the left. Now I think we also know the mass, don't we? So I'll tell you what I'm going to do. I'm going to cheat a little bit. I'm going to erase this M. And I'm going to put the mass in there as well. It was a 10 kilogram block. So that becomes 10 times A. And you can see what's happened. All of the things we knew have become numbers. And the only thing left is the A, and that happens to be the thing that we were looking to find. So the answer always emerges from this nice little net force equation. It's a very useful thing to use because the answer will be in here somewhere. Doesn't matter what the question actually asks for. If it asked for the mass, now we would have an M in here somewhere and all the other things would have turned into numbers. So this works every time. Let's figure it out. 10 times A equals 50, and now we have to do the multiplication here. 3 times 8 is 24, 3 times 9 is 27, and 2 is 2 and 9, and the decimal place looks like 29.4. So we have to subtract 29.4 from 50. Well, we can do that pretty easily. If you subtract 29 from 50, you would end up with 21, right? So 29.4 should end up with 21.6. No, I was right, 20.6. 20.6, that's right, isn't it? 4 is 10, 9 and 1, 2, 4, 5. 20.6 equals 10 times A. And if we divide both sides of our equation by 10, then the answer is pretty easy. We end up with A equals 2.06 meters per second squared. And that's the acceleration of the block, or the box. The answer turned out to be positive. You see how the answer came out positive, which means the block should be moving to the right. And if we look at the picture, that makes sense because that's the way you were pushing the block, to the right. The block certainly couldn't go to the left if you were pushing it to the right. And so you see how we've used the horizontal forces now to add on to our study of the vertical forces, and we've used them both together to find out something about the motion of the block. All right, let's do, a second example. And maybe we'll now do the example I initially was talking about. Let's keep our block the same so that we can still we can compare how things change. Let's just keep a 10 kilogram block here. And of course, we can draw in all the forces that we know. Here's some blue ones, which will be the vertical forces, the force of gravity pulling down, the force of the normal pushing up, and we'll make some green forces here for horizontal forces. There will be an applied force, and there will be a friction force pulling back this way. All right. And I will give you a little bit of information. I'll tell you that the frictional coefficient is 0.3 again, but this time I'm not going to tell you anything about the applied force. And the question we're going to ask is, what applied force is necessary or needed to slide the block at a constant speed? See, in the last question, we put a big force on there, and we saw that the block accelerated, which means it got faster and faster and faster as you pushed it. Well, that's not really how people push things, is it? When you push something, you generally slide it along at a pretty even speed. It doesn't make sense to go faster and faster and faster because you get tired very quickly. So what we want to do is we just want to slide the block along at a nice, steady, constant speed. So let's see what force we would need to apply to make that happen. So our goal is to figure out the value or the number associated with this guy right here. Of course, we have to solve the problem the same way as before. So we'll start with the vertical forces, up and downy forces only. Now let's have a look at what we've got. If we start with vertical, the net force, or the total up and downy vertical forces, F net Y, has to be all of the up and down arrows in my picture added together. And I see two. I see force of gravity and I see normal force. So I put them in here. I don't put any other forces in here because the other forces are not vertical. Fn and Fg. Now, I remember that F net equals ma because of Newton's law. And I remember that Fg is equal to mg. That's the formula for the force of gravity. So then I go down here and I say, what can I put into this equation? Well, I know that the mass is 10, but since we're talking about up and down, I know that this block is not going to accelerate up or down, is it? In fact, it's not going to accelerate anywhere because we want to, even when we push it, we want a constant speed. So there's not going to be an acceleration. So that means acceleration would be 0 for the vertical direction. I know that the mass is 10, so I can put it for this m, and I know g is 9.8, and guess what? This arrow points down. So I'll put a minus in there to show the arrow points down. It's the force of gravity. So 0 equals Fn and minus 98. Notice I have got the very same answer as I did the first time. The normal force is still 98 newtons when I move it over to the other side. So there's my normal force. That hasn't changed. And that's because I didn't change anything with the up and downy part of the question, did I? All I changed was a little bit about the horizontal forces. So let's take our blue pen here, and now let's look at the horizontal lefty-righty forces. For horizontal forces, I write F net x, the sum of all of the sideways arrows. And so we look up here at the picture, and we see that the sideways arrows, there are two of them. There is the applied force that I'm looking for, and there is this frictional force on the other side, trying to oppose the motion. So we write those in. F net x equals F applied plus the force of friction. And it really doesn't matter which one you put first. If you want to write the force of friction plus F applied, you can do that too. Now, we do the same thing as we did before. F net is still ma. But this represents sideways acceleration now. And F applied, I don't know what it is. The question asked me to find it. But remember that the force of friction is equal to mu times Fn. That's how we calculate friction. So the mu was told to me, oh, I'll put mu first. Mu, whoops, that's not mu. That's a crazy looking y. We put mu Fn. And I'll keep the plus sign for now. But in the next step, I'm going to add my numbers. I'm going to put 10 here. Now, acceleration. Well, in the first example we did, that's what we calculated. But here, we're not calculating acceleration. The question asked us what applied force would be needed to move the block at a constant speed. Well, if you're moving at a constant speed sideways, that means that the acceleration sideways is also 0. So there's no acceleration here because of the constant speed, which means I can put a 0 in this one as well. So it's going to be nice and simple, just like the vertical forces. F applied. Now, the friction force goes to the left, so I'll give it a negative. I'll put the 0.3 that was given to me as the mu value, and I'll borrow the normal force that I figured out up here in the first part of the question using the vertical forces, and I'll just put it down here as 98 newtons. And then I can do the rest of the math. So 0 equals F applied. Notice how this time everything disappeared except the F applied, which is what I'm looking to find. And if I multiply this, it still comes to 27, 29, nope, yes, 29. I'm sorry, let me just fix that up. My brain is working slower than my fingers, it seems. So we have 3/8 are 24, 29, and a decimal. Now, what I do is move that to the other side, and apparently my answer is that now I know that this is a force because it says F applied here, so that's newtons, and I write F applied. I've discovered that the force I would need to apply to slide the block at a constant speed is 29.4. Now, in our first example, we were pushing, I think, with 50 newtons. 50 newtons was a lot of force compared to this. This is just about half of that. So the nice thing is that when you push at a constant speed, you can push with less force. 29.4, much less than 50. That's why you don't get as tired. But I want you to look at what happened in our story here. I want you just to look for a minute. It turned out that the applied force, if you look right over here at this part of the story, the applied force is working against the friction. See how the two, this one is positive and this one is negative. So they're working against each other, and you can see that in the picture if you want to look back there. They're in different directions. But if I don't want to have any acceleration at all, if I just want a 0 or a constant speed, then that means that you need to have balanced forces. And the math told me that that's what makes sense here. If the force applied is equal to what was the friction force, see how this was all the friction over here, this side? As long as you match the friction, you can move at a constant speed. So we've actually discovered that in order to slide something at a constant speed, the applied force has to match the frictional force. And that's kind of a neat thing to remember, so that when you're doing a question in the future, you'll be able to remember that, and if not take a shortcut, at least you'll know when your answer comes out that it's supposed to kind of make sense, that it's the same as the friction. So pushing an object at constant speed means you must apply a force that is equal to the force of friction that can work against you.